All right, hello class. And let's see, let me get to blue, and it is blue today. So that's the pen color of the day. So today we're going to do a review of limiting reagents. And this is something going to end of the material before the test. And we'll talk about what we're going to have on the test. And so with this review of limiting reagents, this is kind of accumulation with everything that we're going to be doing today. So why look at this? Because honestly, everything we do from chemistry from now on, we're going to have something that is in small amount, and we're going to add a lot more stuff to it. And we're ultimately going to figure out how much we actually think we're going to make, something called a theoretical yield. And chemists do this because a lot of stuff when we make things, some of the reagents are very, very expensive, and we really want to use that as a limiting reagent. And so a lot of times we do is add other stuff to it to increase the utility and the efficiency of the reaction. And sometimes that means doing it in excess or having a catalyst. So that's the reason why we do this. And you need to remember that the reagents and reactants, those are in the products. So the reagents reactants, in a reaction of A plus B goes to C plus D. The reagents and reactants are these guys. And the products are what we have at the end of the arrow. So before reaction, after reaction. And this is what I want you to, part of the reason why we're going to do this is to focus on that as well. Now, when we look at limiting reagents, we're looking at which reagent or which reactant runs out first. That goes to zero. And when that goes to zero, the reaction stops. It can't go on any further. And so with the limiting reagent process problems, we're looking for how much reagent that limits the reactants. And once we know that reagent, we can figure out what the theoretical yield is. And then we have excess reagent. That's the stuff that remains after a reaction stops. And that's why we filter and do some other stuff to our product flask to make sure we get all the impurities, all the stuff we don't want out. And that, again, remains afterwards. And so here's the process. It looks fairly easy, but it's a little bit more complicated than this, because when we say we convert mass to moles, we need to determine the molecular weight of everything. So every time you get a problem, determine the molecular mass, or the molar mass of all the compounds we're looking at. You may not need all of them, but you need to at least determine the molar mass of the compounds that you're using. And then we convert mass to moles. And then when we do that, we'll convert all the grams of our reagents to figure out 1 molar product. So we convert to moles of a reagent A, and then 2 moles of reagent A makes reagent B, so that's 1/2 of the amount. And we compare that to all the other reagents that we have, and sometimes you may have 2, 3, or 4 reagents, and you got to figure out which one's going to be limiting. And it's one that makes the least. So that, and once we get that, we can figure out theoretical yield and how much of the excess reagents we have. And that's what people hate, is find out how much left. But let's go ahead and begin with this. How do we find the limiting reagent? We have 2 copper plus 1 sulfur makes copper sulfide. So what we have is, we have 80 grams of copper and 25 grams of sulfur. Now do not do 2 to 1. You don't, because we need to convert to moles. And here's the thing, and this is what people have problems with, is that, okay, well, I got masses here. You need to convert to moles because moles is what we count. This, changes the density and stuff like that, and the molecular weight of these things change. So we need to convert to moles. So let's go 80 grams of copper. Let me do it this way. And now, I forgot I had this slide in here. Now, there's 2 ways to do this. I kind of want to find out how much product each reagent can make. This is the way I like to do it, and this is what I'm teaching you. Some teachers compare the amount of reagent you need to react with other completely, and either way you could do it, but with this way that I'm underlined and starred, is you can easily get to the limiting reagent without showing too much work, because you already have it. So let's look at this reaction. Reaction is 2 copper plus sulfur goes to Cu2S. And we have 80 and 25, so we've got 80 grams of copper, 25 grams of sulfur. So this is what I'm going to do. You notice I wrote this down. So I want to convert the grams of copper to moles, so 1 mole of copper. And the molecular atomic weight of copper is 63.55. So now we convert to moles. Now with this type of problem, you only got one product. So I want to convert the moles of copper to the moles of copper sulfide, copper 1 sulfide. Grams of copper cancel. Grams of copper cancel. Moles of copper cancel. And now we've got moles of copper sulfide. So 80 divided by 2. So make sure you go across first, and I do it for those who haven't. So this is 80 mole of Cu2S divided by 63.55 times 2. That's 127.1. You take and then divide that into 80, and you should come up with 0.629 moles of copper 1 sulfide. Do the same process with sulfur. Now what we're doing is we're changing the amount. It's the same thing, but instead of moles of copper, you got moles of sulfur, and that atomic weight is 32.07. And then we change it to moles of copper sulfide. And you can tell from here the molar ratio between sulfur and copper sulfide is 1 to 1. That's where I got these numbers from, 1 to 2. And we figured out what we have. So basically 25 divided by 32.07. You get 0.780, rounded to the 3rd decimal place, moles of copper 2 sulfide. Now, if you look, the amount, even though I have 80 grams of copper, I'm only going to make 0.629 moles of copper 1 sulfide. So the copper is limiting. And to find the theoretical yield, 0.629 moles of Cu2S. And I'm going to find the mass of that. 1 mole of Cu2S. And see, sulfur is 32.07 plus 2 times 63.55, and that is 159.17 grams. And basically you're going to get 100 grams of material. And that's how you solve. So what we did was figure out the limiting reagent, which is this guy. We make 0.629 moles of copper 2 sulfide compared to 0.78, so we still have some sulfur left. Theoretical yield is going to be 100 grams of copper 1 sulfide. And we can figure out how, and you can figure out how much stuff you have left, and we may do that with the other example. So let's look at our other example. And we have the combustion of ethene, C2H4, plus 3 moles of oxygen, and you get 2 moles of carbon dioxide and 1 mole of oxygen. And so we're going to do the same thing. So we're going to start off C2H4, the molecular weight, MW, or the molecular mass. Everybody uses MW for molecular mass, so 12.01 times 2 plus 4 times 1.01. So we should have 28.06 grams per mole. And that's of ethene. Oxygen, 16 plus 16 is 32 grams per mole of O2 per mole of O2. All right. Now, before we do the calculation, we're going to pick a product. Sometimes the problem itself will give you what to look for. Sometimes they'll say we're looking for oxygen or we're looking for carbon dioxide. In this case, I haven't mentioned. So either way, let's look at carbon dioxide. Let's use this to find the limiting reagent. So we're going to use carbon dioxide. And what's the limiting reagent? Theoretical yield based on CO2. So let's rewrite the reaction up here. C2H4 plus 3O2 yields 2 CO2 plus 2H2O. I believe that's correct. Yeah, this is going to have to be H2O. I messed up this problem here, so let's see. 2 times 2 is 4. 5, 6, there we go, 2H2O. Ooh, got that right. So we have 2.7 and 6.3. So we do the same thing as last time. And this time we change to moles. So 1 mole of O2 gives me 32 grams of O2. And up here we had 1 mole C2H4. And that's going to give me 28.06 grams of C2H4. Now we want to convert this to CO2. So for every 1 mole of C2H4, we get 2 moles of CO2. And that should give us so many moles of CO2 at the end. And with this, we're going to, for every 3 moles of O2, we get 2 moles of CO2. Now we got moles of CO2. So that now with this, we'll figure out which one of these is limiting reagent. Now, I want to point out is that when we look at this, you can use H2O. It doesn't matter which one you use. And that is something I want to stress. It doesn't matter which one you use. Sometimes they'll tell you to use one or the other, but a question like this, you don't know. You don't need to know. So 2.7 divided by 28.06. And then multiply by 2. And I'm going to make 0.192 moles of CO2. And over here we got 6.3 divided by 32 grams. times the quantity 2 divided by 3. And I get 0.131 moles of O2. Of CO2 made, excuse me. So this guy here is limiting. Here's my limiting reagent. It makes less CO2, so to get the theoretical yield, 0.131 moles of CO2. Now, CO2 is going to be 32 plus 12, 44.01 grams of CO2 per mole, and you can check my math. And the amount that we're going to get is going to be 5.78 grams of CO2. Now, I want to point out is that we know oxygen is limiting. So this is our limiting reagent, O2. Theoretical yield is this guy. Now, how do we know how much is left? And that's going to be C2H4. So and we're looking for C2H4 because that's in excess. And there's several ways to do this. And one way is to take the 6.3 grams, excuse me, for flipping back and forth, of O2, multiplied by the molecular weight, which is 32 grams per mole. Then we're going to multiply by I'm going to flip back to this, we're going to multiply by the ratio of C2H4 to O2, which is 1 to 3. So 1 mole of C2H4 goes to 3 moles of O2. Remember, this is O2 and this is O2. And what we're going to get with this is how much is used. It's used up. So 6.3 divided by the quantity of 32 times 3, and you're going to get 0.0656 moles of this used up. Now, to find how much is in excess, we go back take the 2.7 and figure out the moles of this that we're going to make, that we have. So that's 1 mole of C2H4 divided by, did I say 28? 28.06. And so we do that math, divide by 28.06, and you're going to get 0.0962 moles of C2H4. That's what we have initially. Here's the thing, I haven't really changed the calculations that bit. What I'm doing is changing what we think, what each equation means. To get what left is 0.0962 minus 0.656. And we're going to figure out how many moles of this is left. Let me get that clear. 0.0306. And that is what is left. And that's moles of C2H4. All right, guys, hope you understand this. If you have any problems, please give me a call or email me, contact me in some way. Thank you.